Sparkle presentation today. It was really good. This is a variation on that, kind of like a distant cousin, I would say. Here's how the game works. A player begins his or her turn by rolling 10 dice. After rolling 10 dice, the dice are scored according to just 3 rules. First off, 3 of a kind n is worth 100 n points, except 3 ones count as 1,000 points. So for example, 3 threes count as 300, 3 sixes count as 600, except ones are the best. 3 ones count as 1,000. Secondly, after the triples have been removed, the ones are scored as 100 points each. There might be 0, 1, or 2 ones. And then in a similar fashion, the fives are then counted, and they're worth 50 points each. Right. After a player has rolled and removed all the scoring dice, the person has a choice. Either keep the points that they have and end their turn, pass the dice to the next person, or on the other hand, they can roll all of the non-scoring dice and try and add points to their score. If a player does continue rolling, similar to Fargo, there's 2 ways it could end. The first way, the sad way, is if a person re-rolls some number of dice, 2, 3, 4 dice, whatever, and they score 0 points, then not only is 0 points added to their score, but their run score is worth 0, and their turn is over. Okay, so that's the sad way of ending. On the other hand, a run could end by using up all 10 dice. If a person is successful in using all 10 dice, then they get to keep the points that they've scored from those 10 dice, and they get 10 more dice. And that's a good thing. So just to make it really clear, here's an example turn. Let's say a person begins their turn by rolling 10 dice. They've got 2 ones, that counts as 200 points. They've got 3 threes, that counts as 300. And there's also a 5 there, that'll count as 50 points. So this person has 550 points, 4 dice, and a choice to make. Either roll the 4 dice and try to increase their score, or stop, end their turn with 550 points. Let's say this person rolls and they've got 4 dice. This time they got a few more points. They got 150 points there from the 1 and the 5, with now another choice. Roll the 2 dice, or play it safe and end the turn with the run score of 700. This time, the person keeps going, doesn't work out so well. Rolling 2 dice, this person gets a 3 and a 6. That counts as 0 points. There's no triples, obviously, no 1s and no 5s. And so not only do they have to end their turn, but they end their turn with 0. Right? A game of Fargo can be played with any number of people, and the game ends as follows. Once one player ends their turn with 10,000 or more points, everyone else gets 1 more turn, and then the game is over. Now, I found out the first time I played this last fall that it is possible to do spectacularly bad. I found out it can be very bad to be too aggressive, and I ended up with 0, about 12 rounds. So naturally, that led me to a number of questions. Why am I so bad at math? Why am I studying math? Why do I not understand probability? But then some questions that I actually can answer for some of us today. How many strategies are there? What does the strategy space look like? What's the expected value of the strategy? We'll go over that question briefly. And then most importantly, what strategy is the best? And by best, I mean maximizing the expected value. So let's talk about the strategy space for a sec. Okay? A few observations. First off, if a reasonable strategy continues rolling with n dice remaining and p points, then it should also continue rolling with less than p points. Okay? So for example, if I've got 5 dice remaining, and I decide it's worth it to risk 500 points and keep rolling, then if that strategy is consistent, it should also be willing to risk 450 or 400 or 350 points, any number less than 500. A second observation is that we don't need to worry about more than 8 dice. The worst possible roll would be a 2, 2, 3, 3, 4, 4, 6, 6. That only uses 8 dice and scores nothing. And so if we've got 9 or 10 dice, or more than 10 dice somehow, we don't need to worry. We should always keep rolling. There's no risk involved there. Okay. Let's take a look a little bit more at the strategy space, looking at the minimum and maximum possible scores. Let's just look at this row here. What this is saying is, with 8 dice remaining, that means a player has used up 2 dice. And so the minimum possible score they could have is 2 5s, which counts as 100 points. The maximum possible score is 200 points if they get 2 1s. And if we continue that pattern up to 1 dice remaining, we get this 3. This can be then formulated as follows. A reasonable Fargo strategy can be written down as a vector of 8 numbers, where the ith entry indicates that with I dice remaining, a player should continue rolling unless their score is at least x sub I. All right, and this will be easiest with an example. So consider this strategy vector. What this says is in the second entry, we have 600 points. So the way of interpreting that is with 2 dice remaining, keep rolling unless the run is worth at least 600 points. Okay, that'll be the cutoff point for a consistent strategy. Again, that's with 2 dice remaining. A nice thing about this is since we have the maxima and minima for each entry, it's possible to write down a number such that we should always stop rolling. So the most conservative approach with 1 die remaining is 450. Similarly, on the other end, the most aggressive strategy, since you can only score up to 200 points with 8 dice remaining, the most aggressive strategy there will represent as 250. All right. So our first question is, how many strategies are there? And using this formulation, it's really easy to just take the product using a little combinatorics, and we arrive, if we take the product of that column, we arrive at 66 billion possible strategies. A lot to look through. There we go, there's our first question. Now, unfortunately, for the sake of time, I'm going to have to go really quickly through this second question. There's a lot here, but basically, I'm going to boil it down to this. There's a nice algorithm. It's a recursive algorithm, and it can be programmed pretty easily. I used Python. This is a brief preview of what it looks like. All right, but unfortunately, we have to move on. But basically, the idea here is given a strategy vector, we can determine what the expected value is for a turn using that strategy vector, all right, including the probability of using all 10 dice and getting 10 new dice. All right, but really, what we really care about is the third question: which strategy is the best? And I decided to take a kind of a different approach to try to figure this out, and that is a genetic algorithm. Genetic algorithms were introduced in the 1970s by a mathematician by the name of John Holland from the University of Michigan. And what a genetic algorithm does is it explores a large solution space by mimicking the process of natural selection. You'll see a lot of biology terms come up here in just a second. And it's had a lot of interesting applications, particularly in machine learning and some engineering problems. All right, let's talk about the genetic algorithm. In order to do a genetic algorithm, we need 3 ingredients. The first thing we need a way to write down all of the members of the population. We need a way of encoding all of the genetic information. And for that, we use the strategy vectors, the lists of 8 that I talked about earlier. The second thing is we need a way to evaluate how strong is an individual from the population, how good is a strategy, in other words. For that, we use the expected value function. And then finally, we need some rules for genetic succession, which are right here. So here's the way the procedure works. Step 1, take 1,000 random strategy vectors. Right? We can't look through all 66 billion very efficiently, but we can pick 1,000 of them and evaluate them pretty easily. The next thing we'll do is we'll sort them according to how fit they are. We'll sort them by their expected value, and then we'll start building a second generation. Okay? Throw away the 750 weakest individuals, and instead we'll abide by the survival of the fittest principle. Take the 250 that are strongest, and we'll use those to build up the next generation. We'll throw in some randomness with by adding some more random strategies. We'll also throw in some mutation by randomly mutating a few entries from the vectors. And then what we'll do is we'll take all the things we have and we'll randomly recombine them until we have 1,000 strategy vectors back, until we've re-reached our starting population. That works to get from the first generation to the next. And if we keep repeating that, the idea is that the strongest genetic information, the strongest strategies, will spread throughout the rest of the population, and we'll end up with some good results. Okay, let's take a look here at the results. What this shows is the results from 100 trials. Each trial took a population of 1,000 strategies, and it performed the genetic algorithm over 25 generations. And what we see here is some good things. First off, if we look at the red here, this shows the average expected value of the population. And we see here that it starts pretty low, and then it plateaus over the course of really just a few generations. 25 is more than sufficient to get that up to a reasonable level. But what we care about the most is what's in the blue here. Again, we want to find the very best individual from all of the possible strategies that we have. So let's zoom in here. This graph shows the same x-axis, 0 to 25 generations, but now the y-axis is zoomed in. All right, from 960, sorry, this is a little small, but this shows 960 here, and all the way up at the top it's 963. So this is a really compressed y-axis, and what we see is that the strongest strategies from each generation seem to be converging to something. All right? And to make sure that we're not stuck in some, maybe there's more than one optima, or maybe it's stuck in a local optimum, let's take a look at what those look like. The maximum expected value was this number here, 962.33. And it was attained in 8 out of the 100 trials. So not a ton of the trials, but it was attained in 8 of them. And what's most important is that in all 8 trials, it used the same strategy vector, right? Indicating that we're not getting stuck in a case where there's more than one solution, or a case where there might be a local optima or something like that, okay? So it looks good. It seems to be converging to one point. Moreover, in a further analysis, among the strongest vectors from the trials, from all of the trials, not just the ones that got to this one, the average strongest vector at the end was 2.42 steps away from this, where by a step I mean just incrementing by 50, or going up or down by 50. Okay. And the very worst strategy that was the strongest of one of the genetic algorithms was still only 7 steps away, which is not too bad. Lastly, let's just take a look at the strongest vector a little bit. Let's define the aggressiveness as follows. For each strategy vector of 8 numbers, x1 to x8, we'll define the aggressiveness of the strategy as the vector a1 to a8, where each a sub I denotes the fraction of possible values for x sub I that are smaller than x sub I. So if we take a look at our best strategy, we're pretty sure it's the best, that's here. And this shows the aggressiveness. Okay, so a 1 indicates that it's the most aggressive strategy, and a 0 indicates the least aggressive strategy. And what we can see from this is it's matching a lot with the intuition. With 8 dice, the chances of increasing your score are really good. The chances of losing all your points is really small. And so this indicates we should always keep rolling. That's what that 1 means. On the other hand, with 2 dice, what this is telling us is we should always stop rolling. It's so risky when you've got 2 dice, even if you could increase your score by a little bit, even if you could use up both of the dice, your expected value won't be increased if you continue rolling. And probably the most interesting case is this case with 4 dice remaining. What this is indicating is if we have a score of at least 1,150, we should stop rolling with 4 dice. But if we've got a number less than that with 4 dice, it's worth keep rolling, even though it is somewhat risky. We can also picture this as a bar graph, again showing with 5 to 8 dice, we should always be aggressive. We should show maximal aggression. With 2 dice, we should not be aggressive at all, and then sometimes even better. There we go. We've addressed the questions. And finally, let's just talk about some conclusions. The genetic algorithm does a really good job at not getting stuck in local optima, which is really pleasing. It seems to be converging really nicely. The biggest problem with it is we're not really sure if it's found the very best solution. It doesn't seem to hone in on one particular value, and so with more tuning, we could try and improve that. The other thing that's really nice about the genetic algorithm is it seems like it'll extend really nicely, really naturally, to cases where we throw in multiple players, or when we talk about the endgame scenario where we're not trying to maximize the expected value, but rather the chances of winning. Thank you so much again for coming, and are there any questions? Yeah.
In the game, when you do a roll, do you have to take all the points that are available?
Yes, so unlike Fargo, there's a multi-split. You can keep a few there.
Because I'm saying like
reroll it.
3 1s and a 5.
Exactly.
Yeah, don't take the 5.
With Fargo, it's a binary decision tree. So you either reroll all the non-scoring dice or go.
And you have to keep the score.
consider, or did you at all, seeding a future algorithm, or using the same algorithm, but seeding a future culture with like taking your best strategy, putting it in first generation, and seeing where it went from there?
Taking your best strategy, seeding the first generation, you're saying?
Yeah, just have it in there somewhere, and then since it should end up at the top, it should stay there the whole time.
Yeah, yeah. I didn't do that. I think in a lot of ways that would be similar to just extending out past 25 generations.
Right.
And I did try a bunch of different lengths of generations, up to 100 generations. And I got similar results.
Okay.
It seemed to converge pretty well. Good question. Yeah. I love that. Yeah.
I'm gonna take the last question.
Sure.
How come you should roll if you have one die remaining?
Yeah.
But two, you have zero. Because I mean, in Fargo, if I have one die, I only get a 1 or a 5. There's only a 2/6 chance they have to gain some more points.
That's a great question.
So like, two die, I have a better chance of doing it.
The reason is that there's a huge payoff if you go through all 10 dice. If you go through all 10 dice, the payoff is you get to keep all of your points, and you get 10 new
And you
dice.
get to roll again.
And 1 is a lot closer to 0
Yeah.
than 2.
Gotcha.
Good, yeah, good question.
Well, let's thank our speaker again.